So let's look at an example that doesn't involve processing a corpus of documents. So let's think about how to implement the join operation that we learned from the relational algebra in MapReduce. Okay, so here recall that you're given two relations, and a relation is a set of tuples, right? And you're trying to find every record in one relation that corresponds to a record in the other relation, right? And so here we're going to join on SSN equal to imp SSN. And actually, it wasn't quite correct for me to leave this unspecified. There's a notion of a natural join that would match it up if the field names, if the attribute names match, but here they don't, and so I need to be explicit about what I'm joining on. Okay, and so the output here is these three records. Okay, this record joins with these two, and this record joins with this one. Fine. Now, imagine that both of these relations are huge. Okay. So the map phase here is going to process every tuple in general. And we have a problem right off the bat that join is a binary operation, right? It has two input relations. The left relation and the right relation. You're trying to find corresponding tuples in one and the match the other. But MapReduce is a unary operation. It processes a single data set. So how can you, to a first approximation, you can't express join in MapReduce, period. But that's okay. There's a bit of a trick here, and the trick is, look, it's okay that imagine the data set here is just a big jumble of tuples. It doesn't matter what table they came from. We just lump them all together into a single data set called tuples. Okay, and that'll be what we process with MapReduce. Okay, and so here I'm asking the question, what is this for? Well, this is a label that we've attached to every tuple so that we can know where it came from, and we'll see how that's used later. Okay. Now, I'm not being specific about where you get this label or how you do it in MapReduce, but I want you to think logically that it's necessary. And in practice, it's not that difficult, right? Because for example, if you're processing, you have distributed files from this directory representing all the employee chunks, and you've got distributed files in this directory representing the assigned departments chunks, you can look at the file name to tell what table it is. And so in the map function that you write, you can determine that, aha, this has file name, this has the employee relation name in its file path, and I'm going to go ahead and attach that as part of the record. Okay. And so we could write pseudocode for this, and in fact, you might as part of the an upcoming assignment. All right. So fine. So what's the map phrase look like of this relational join? Well, for every record on the input, you're going to produce a key-value pair. We know we have to produce key-value pairs because that's how MapReduce works. So what's the key going to be? Well, I'm going to give you, the key is going to be the join attribute, the attribute that you're joining on. And the value is going to be sort of everything else, right? The rest of the tuple. And we can actually get away with removing this guy to save some space, but typically you wouldn't bother. Okay. So fine. So given a tuple that looks like this with three fields, we produce a key of 777777 and so on, and the value is the entire tuple, and so on. And again, notice that both the tuples from both relations are all lumped into the same input. All right. I may be belaboring this, but I want to make sure that's clear. Okay, so far we've done two tricks. One is lump everything together, and two is produce a key-value pair where the key is the join attribute. Now, what happens in the magic shuffle phase? Well, everything with the same key gets lumped together, as we talked about, and so now you get a reducer invocation that has one reducer invocation for every unique key. So in this case, it'd be 1 for 999, so on, and 1 for 777, so on. And the list of values associated with that key will be all the tuples that share the same join key. Now, it doesn't matter what relation they came from. They'll all be in this list. So in this case, we get one tuple from the employee relation, and we get one tuple from the department relation. And here we get one tuple from the employee relation, and we get two tuples from the department relation, right? And so now, in the context of a single computer, we have everything we need to compute the join. And further, each one of these reduce invocations can be done on a separate machine. Okay, and that's how we scale. So now this reduce function that the programmer would have to write if you're implementing a join phase would have to take this key and take all these tuples and produce the joined tuple, right? Where these two attributes came from employee and these two attributes came from department. And same thing here. Employee, department. Now, if you want to think about what kind of operation you need to implement in this reduce function, well, you've got a set of tuples from one relation, and you need to associate it with every possible tuple from the other relation, right? Because we know they all join. They're all, by definition, they all join. They all have the same key. They all match. So if you have every member of a set paired with every possible member of another set, if you remember, that's a cross-product operation. And so here again, we see relational algebra popping up sort of in a different context. Okay. So I don't want to confuse you too much, but the overall operation we're trying to do is implement a parallel join. It happens to be that locally, right here inside one reduce function, we recognize, aha, that's another relational algebra operator, a cross product. But this is more for abstraction purposes than for algorithm purposes. Just want to point that out. All right. So again, you put on your relational algebra colored glasses and the whole world, these operators start to pop up everywhere. All right. So fine. So let's do this one more time just to make sure it's clear. So I'm giving you two relations, order and line item, and they have these fields, an order ID, an account, and a date. And here there's an order ID, an item ID, and a quantity. And we're going to join on order ID. So what's the map phase look like? Well, once again, the key will be the join key, in this case order ID. And the value will be this pair, the relation name along with the original tuple. And before we just sort of lumped these together in one tuple, and it doesn't matter very much. Here I've kind of structured it slightly differently, but the point is that all the information is here. The key must be the join key, and the value is the tuple as well as some sort of indicator of what relation it came from. In fact, maybe I'll ask real quick, why do I need that indicator of the relation? Well, in the reduce phase, I wouldn't be able to produce the join tuples properly if I didn't know which tuples went with which relations. If I just had a big bundle of tuples and I couldn't really figure it out very easily, that would be a problem. Theoretically, you might be able to avoid tagging it explicitly with employee and department because you could deduce that, well, the employee table is the one that has a string first, followed by the join key, and the department relation has the join key followed by some other string. But it's a little dangerous to rely on that kind of information because you could be joining two tables that have exactly the same schema, and there wouldn't be any real obvious way to figure it out. So an explicit tag is a little bit safer here. All right, fine. So that's the map phase. Process we lump all the records together and produce key value pairs where the key is the join key from the corresponding relation, join attribute from the corresponding relation, and the value is the entire tuple tagged with the relation name. Okay. And there it is right there on the slide. Okay, so what's the reducer look like? Well, now we've got all the tuples that share the same key together, and it will produce these join tuples. It will join this order tuple with both of these line item tuples to produce these two join tuples. Okay. Fine. So now let's go on to a different example. And so here, maybe we're going to get started with analyzing a social network. So here we have a graph where every edge represents let's say a friend relationship. Or if you're thinking about Twitter, you could have this be a follows relationship. And so the input here is a set of edges with the semantics of Jim is friends with Sue or follows Sue, and Sue is friends with Jim or follows Jim, and so on. And so one point I'm making here is you'll notice that if Lynn points to Joe, then Joe points to Lynn, and so there's a symmetric relationship here. Okay. And I've done that for simplicity's sake to sort of avoid the confusion that can result from thinking about undirected graphs versus directed graphs. Okay. Fine. So anytime you see an edge going one way, you'll see the other edge coming back. Now, what we want to do here is, well, before I say what we're going to do, let me make sure the task is clear. We're going to count the friends. We want something very simple. We just want to say, how many friends does Jim have? And how many friends does Sue have, and so on. And so the desired output here is Jim with 3, because Jim has Sue as a friend, and Jim has Kai as a friend, and Jim has Lynn as a friend. And we want to have Lynn equals 2, or Lynn has 2 friends because Joe and Jim, and Kai is just 1, right here, Jim, and Joe is just 1, which is right here, Lynn. Okay. So this should already look like something we've already done before. So it happens to be social network analysis, and the records happen to be these, pairs of people, but the algorithm you're going to use should start to stand out to you. Okay. And maybe you'll see why in a second if it's not clear. So in the map phase, how are we going to do this? Well, for every friend on the left-hand side, produce a key value pair where the key is the name of the friend, or the name of the person, and the value is just the number 1, indicating that there's exactly one friend associated with that. Sorry, exactly. That we've encountered one friend associated with, say, Jim in this case. All right, so this record gets turned into Jim in 1, and this record gets turned into Sue in 1, and this record gets turned into Lynn in 1, and so on. Okay, and then through the magic of MapReduce, the shuffle phase produces this intermediate result where we have Jim, the key, associated with a list of occurrences, 1, 1, and 1, and Lynn is associated with 2 occurrences, and so on. And then the reduce phase just simply adds up all these occurrences. And so what does this remind you of? Well, it's a lot like the word count example, right? Instead of documents producing words and counts, it's even simpler. It's for every record, just produce a single count for that for that person that the record represents, the person on the left-hand side. Okay. And after that, the reducer is literally exactly the same, right? It'll add up all the occurrences and produce a single number. Okay. So in the next segment, we'll talk about something a little trickier, which is implementing matrix multiplication in MapReduce. All right.